it's a new camera.
Yes.
Small one.
It's improving every time.
It's perfect. Candid camera size.
Yeah.
Yeah.
Ouais, c'est bon, ça stream.
Ok.
Cool. So, are you set with your family, John, or?
Yes. Yeah. They are living here, so it's
Okay.
quite easy.
Yeah, that's nice.
And you have your rugby team.
I think
Teammates.
just one,
Ah, yeah.
yeah, one is coming. And they're working. Il a mis des trucs. Ah, il a mis du scotch. Du scotch blanc. C'est bien.
Ah oui. Réglage. Réglage. Réglage.
Peut-être il était très haut, non?
Je sais pas pourquoi c'est penché.
Vérifier dessous, arrêtez.
Ah oui, mais même sur règle, c'est penché quand même.
Ça augmente la hauteur, mais ça reste un peu léger.
J'arrive plus à monter par mon descendre.
Baisse le pied.
Encore bah, justement, ça peut être très bien.
Il faut que je supprime l'essai qu'on a fait tout à l'heure.
Et puis, c'est bien penché. Et bien, c'est pas bon.
Amaya,
Oui.
sur cet ordinateur-là, est-ce qu'il y a il y a toujours Outlook qui est ouvert ou pas? Je pense que tu peux le fermer s'il est ouvert.
Je ferme.
Ouais.
Voilà.
Et donc normalement après il est en mode sleep et il y a les diapos de Katia. Je sais pas si t'as
Je les mets maintenant, tu penses, sur le bureau, comme ça?
ouais, alors il faudrait que ça soit. Oh non, remarque, oui, ça peut être là-bas en fait, ouais, tout à fait. Ouais.
Comment?
Ça peut être diffusé là-bas, ouais, en effet.
Ah, mais là, c'est cet ordi-là.
Ouais, mais je pense que c'est pas trop grave. C'est juste, ça sera juste pour quand elle posera les questions, de switcher.
Sinon, on peut faire avec ça, vu qu'il n'y aura plus besoin de celui-là pour les
Ouais,
questions.
tout à fait, ouais.
Donc, c'est toi qui vas mettre le diapo de Katia quand tu poseras les questions. On met sur le bureau, et puis on...
Ouais.
Du coup, on n'aura plus besoin de celui-là.
Nickel.
Bla bla bla. Secondes. Il y a 10 secondes de...
Ah oui?
Ah oui, c'est normal.
Ouais, ouais.
S'il y a un attentat, j'aurais le temps de couper. Bon, vous me direz bien à la fin quand vous voulez couper les micros.
Ouais.
Vous voulez après le retour, je coupe juste les micros et puis pour enregistrer jusqu'à la fin ou on coupe tout?
Ouais, on coupe tout. Ouais. Une fois que Stéphanie et moi on a parlé, on a fait le truc et qu'on demande à tout le monde de partir, on coupe.
Vous voulez pas un peu de lumière là, c'est un peu sombre.
How are you feeling?
Me?
Yeah.
It's okay, it's a bit like the rush. That's fine, everything is working, so...
Good.
It's just my family. I'm coming back.
It's on camera?
Mhm.
Are we also on camera?
Yeah, so
Ça fait un réflecteur.
ah. Oh yeah, and the tiny camera as well.
Yeah.
Soi-disant 0,01 lux. 0,001 lux.
Ah ouais?
Mais bon, j'ai pas trop de différence avec l'autre.
Et que c'est Gauthier qui fait
Ouais.
les diapos.
Dispositif.
Ah ouais, mais là,
Ah ouais.
c'est.
Bon, ton objectif, c'est de faire 1 million de vues sur YouTube. Hein. Si t'as pas ça, t'as pas la thèse.
Il y avait like en direct.
Ouais, c'est clair.
Yeah, the objective of Amaya today is 1 million of views on YouTube. Otherwise,
Yes.
no PhD.
That's a good goal.
Mais comment c'est penché comme ça?
Faites gaffe, hein, le streaming est en cours, hein, donc si vous dites des bêtises, direct.
Ouais, c'est le réglage de l'angle qu'il faut modifier.
Ouais, mais oui, c'est tout seul dans le jeu.
De l'angle. Ah, sur un côté, il y a. Ah, ça, je l'ai pas.
Ouais, ça bouge. Bouge pas de la tête. Ça fait un peu en 3D. Oui. Très bien. En même temps, c'est moins stressant que de faire un match de rugby avec le maillot vidéo sur les épaules.
Bah, justement, je pensais, mais c'est quand même plus stressant.
Tu vas le coup d'orange.
C'est pas la même ambiance.
Ouais.
C'est bien installé, Mathieu.
Impeccable. J'ai ma petite barre là, elle est bien placée.
Mais dans,
Petit coussin.
dans 2 heures, il va devenir tout blanc, tu vas voir.
Il aura le sang monté de la tête.
Ce sera le moment où il faudra venir derrière et lui le faire entier.
Ouais, il est parti Amaya.
Sur son particulier.
Ouais. Oh, Will. Non, ah oui, ok, ça va. Il y a un retard sur l'écran. Hi, Will. Pretty good, you. Good morning. Thanks. Do you have a coffee? I hope you are early bird. It's not too early for you. Okay, oh good. Oh, yeah, so we could have 30 minutes before.
So when we are doing the round of introductions, are we going to have their faces also on
Yeah.
the screen?
Oui, Amaya. Ouais, quand, au début, quand les jurys vont se présenter, il faudrait qu'on ait les...
Mais c'est pas moi qui gère. Ouais, c'est la petite signature.
Ok.
Là, tu peux mettre en.
Il va être complet.
Avant, là.
La mise
Ouais.
Ouais, voilà, ça c'est bien.
Pas tout le monde.
Ouais, tu peux mettre comme ça, ouais. Celui d'en dessous, aux galeries.
Ah, tu l'as?
Ouais.
Comme ça?
Ouais.
Yeah. Will disappeared.
Yeah, we are.
He's had enough.
Where is Will? We don't see him.
Is Stephanie going to attend?
Yeah, she will join.
Yeah. As well.
Okay, yeah. That's why. Perfect.
Ils sont combien à distance, 3?
Non, il y en aura, il y en aura 2 autres en plus. 3 autres, pardon, en plus.
Are you coming?
Yeah. Ah, peut-être pas, ouais.
Hi Stéphanie.
Good morning. Perfect. Don't fall asleep. So yeah, we just need Nicholas. The cafe gourmand was a little bit too much. I'm feeling asleep. Hi, Nicola. Can you hear us? Yeah, perfect.
Minutes?
Yes, 3 minutes.
It's too long. Supposed to sit here when I do the opening.
Yeah, you can stand up if you want, but
It's a bit strange because the audience is there.
yeah, usually yes, we stand up and we look at the public, but it's kind of strange here. I will try to stand up as well, but one minute.
Okay.
Yeah, I think we can start. Yeah.
Good afternoon, everyone. I'm your chair today. My name is Katja Enberg. I'm a professor in biology at the University of Bergen in Norway. And it's my pleasure today to lead you through this event. And also, I'm also one of the examiners of Amaya's thesis. So I think I now announce this event open. And I would like to ask the members of the jury to present themselves. So we can start with Marie.
No, I think it's okay in English. Thank you.
Thank you, Marie. And then we can take Nicolas. Thank you. And then William. Thank you. And in my stress, I forgot to tell what I work on. I work with evolutionary ecology, individual-based models, and fishing-induced evolution. So now I think it's time for Amaya to take the floor for her speech.
Thank you, Katja, for the introduction. So hi everyone, thank you for being here. And I'm glad to defend my PhD today on the adaptation, persistence and management of Atlantic salmon in a metapopulation context that I completed at the EcoBiome Lab under the supervision of Mathieu Bureau and Stéphanie Carson. And I would like to thank the jury for evaluating my work. So to introduce my PhD, salmonids are fish species that are distributed all over the world, and they are important resources for the ecosystem functioning, but also for human societies. Indeed, they have a strong cultural, but also fisheries importance in recreational fisheries, and also an important economic interest in commercial fisheries, especially in North America. However, these species are threatened, and we can see a decline of some populations that are exploited. For example, in the case of Atlantic salmon, in the south of its distribution range, we can see a clear decline of the distribution of colonized rivers in France across the last centuries, but also a decline of the prey fisheries abundance that are measured in southern Europe across the last decades. Indeed, these species are facing several threats, such as exploitation, barriers to migration, habitat destruction, pollution, or even climate change. And so there are two challenges for scientists. The first one is to better understand their capacity of response to these several pressures, and the second one to provide recommendations for management that are conciliating both the conservation and the exploitation of these natural resources. And so in my PhD, I tried to explore these two questions by focusing on the case of Atlantic salmon. So I tried to tackle these challenges by using a conceptual framework that was introduced by Webster and colleagues. And within this framework, we can identify two main components of the stability and the adaptation of a set of populations. First, we can identify biocomplexity, which can be defined as the population asynchrony or the diversity of life history traits within and among populations. And this biocomplexity is known to favor the stability and the adaptation of populations via what we call portfolio effects. So portfolio effects occur when there is a diversity of response of populations, and this favors the overall stability of the network. However, if populations become synchronous, so they have the same dynamics, the overall stability of the network is reduced, and you can see a lot of variations of the dynamics of the overall network. So these portfolio effects have been largely studied, especially in Pacific salmon, on populations that are exploited or hatchery supplemented, which can reduce their biocomplexity. However, the second component of this framework, dispersal, is less appreciated in the case of salmonids. So dispersal can be defined as the movement of individuals between habitats and between populations with the potential for gene flow, and this will form what we call a metapopulation. So via this movement of individuals between populations, dispersal can provide rescue effects, such as demographic rescue, when immigration increases the population size, genetic rescue effects, when immigration increases genetic diversity within the population, which can limit inbreeding depression, and evolutionary rescue effects, when immigration can provide adaptive alleles to the population. Negative interactions can also occur between these two components. First, dispersal can have homogenizing effects on diversity, and local adaptation can also reduce the reproductive success of immigrants. So during my PhD, I tried to understand the capacity of response of Atlantic salmon by using this framework of adaptation network. So you can wonder how does this framework applies to the case of salmonids, because they are known and emblematic for their behavior of philopatry, which is also called homing. Indeed, you can see on this life cycle and on these quotations from International Organization of Salmon Conservation that individuals are born in river, then they will migrate to the sea to grow, and then they will come back to the river to reproduce. But most of the time, we say that they return to their natal river, so what we call homing. However, some individuals are dispersing to other rivers when they come back from the sea, that we call dispersal or straying. But this behavior is often mentioned as a mistake, like strayers, rather than an alternative strategy of homing. And it is also never represented on life cycle illustrations. When I performed a literature review on this topic, so over several species of salmonids using the keywords dispersal, straying, and gene flow, I found 311 studies, but only a few proportion of them, the yellow color, estimate dispersal on wild populations. Most of them are estimating genetic differentiation in blue or dispersal from hatcheries in red, and hatcheries generally show higher dispersal rates than wild populations. Then, among these studies estimating dispersal in wild populations, the most common metric which is used is gene flow in the brown color, and due to variations in the reproductive success of individuals, gene flow does not provide a comprehensive view of dispersal patterns. And lastly, this literature review highlighted that only a few proportion of studies are discussing the implications of dispersal for the conservation and management of salmonids. Yet, dispersal and this metapopulation functioning can have implications for the understanding of population dynamics, because it can play on this eco-evolutionary loop within populations. Via immigration, the dispersal can change the population density, for example. Via gene flow, it can change the genotypic composition of the population, and this will influence the evolutionary processes within the population. And in return, this new state of the population can influence dispersal patterns and the rest of the metapopulation. So the first objective of my PhD was to demonstrate the implications of dispersal and diversity on the eco-evolutionary dynamics of populations, their stability and adaptation, that I explored in the two first parts of my PhD. And then we can also wonder what are the implications of dispersal for the management of populations. For example, we can imagine that applying one conservation action on one population will influence others that are connected. Actually, there is only a few work explicitly comparing management strategies of metapopulations, and especially with an evolutionary perspective. So these questions remain open, and especially in the case of salmonids. That's why the second objective of my PhD was to investigate management practices that are considering this metapopulation structure and they are conciliating conservation and exploitation objectives that I explored in the last part of my PhD. So we can imagine that we could explore these questions by using different approaches, such as experiments or fieldwork. But in the case of salmonids, it would require a very large spatial and temporal scale, which is almost impossible. That's why I used a modeling approach in my PhD. So models are simplified representation of the reality of a system, but they are based on empirical knowledge that we can get from experiments or fieldwork. And they are very useful to address these issues of large spatial and temporal scales, because we can do virtual experiments by comparing different scenarios and by running many simulations. In the case of metapopulation, different modeling approaches are existing to represent metapopulation dynamics. First, patch occupancy models have been largely used to simulate the demographic dynamics of populations. Then more process-based models, such as life cycle or agent-based models, can be used to simulate the demographic and phenotypic dynamics of populations. But if we want to go further in the scale of processes represented and to study the evolutionary dynamics of populations, we have to include the genetic basis of traits. And this leads us to this type of models, which are called demogenetic agent-based models, so DGABMs. And so these kind of models can represent evolutionary dynamics by modeling the interaction between these different levels, demographic, phenotypic, and genotypic levels. That's why I use this modeling approach in my PhD. So more specifically, I took advantage of an existing model, which is called IBASAM, for individual-based Atlantic salmon model, that was developed in 2012 by Cyril Pio and Etienne Prévost. And this model was developed to simulate one unique population of Atlantic salmon by gathering all the knowledge we have on the species from the literature and from long-term monitoring. Especially in France, in Brittany, we have one river, the Scorff, which is monitored since the 70s and which gives a lot of information on, for example, the size or the abundance of different life stages, which is very helpful to calibrate the model. So as I said, this model is individual-based, so it represents the life cycle of each individual between the river and the sea. So first, individuals emerge from the gravels in April. Their survival and growth is affected by environmental effects, so temperature and flow, but also via competition, which is represented by density effects. The growth of individuals is also influenced by an intrinsic growth potential. Then individuals face life history decisions, such as smoltification or migration to the sea. This decision is based on a reaction norm, which is dependent of the size of individuals, which allow us to represent plastic response of individuals to their environment. We also have the genetic basis of traits, in particular of growth potential and maturation thresholds. Indeed, maturation in river and at sea is based on an environmental threshold model, which depends, so the decision depends on both an individual threshold, which is genetically based, and an individual state, the plant reserves, allowing us to represent both genetic adaptation and plastic response to the environment. Lastly, when individuals return from the sea to the river, we also have selective exploitation, which can be induced, and sexual selection during reproduction. And finally, the genetic transmission of traits to the next generation ends this life cycle. And so overall, with the different processes that are integrated within the model, we can have an optimum of traits that are emerging from the model. For example, here you can see the optimum of growth potential, which is emerging from opposite effects, opposite relationship between river survival, sea survival, and growth. However, this model, as I said, was developed to simulate a unique population of Atlantic salmon, and so we extended it to a metapopulation structure by including a dispersal process between populations. And a genetic study highlighted that the Scorff population was part of a metapopulation, and so we based our model on this spatial configuration of Brittany and represented 15 populations within the model. But it is important to note that the objective was not to precisely simulate the dynamics of the populations for Brittany, but rather to base our model on something realistic. So the dispersal process is quite simple in this work. It is parsimonious. First, we define a constant rate over space and time. For example, 20% of dispersal. But due to size differences of population size, we can still have asymmetric flows of individuals between populations, and it can also lead to different immigration proportion. Dispersal is random, which means it's not dependent on the phenotypes or the genotypes of individuals. And the choice of the population of destination is based on distance with the dispersal kernel and also on attractivity, which means that individuals will be attracted by populations, by rivers with a large carrying capacity. So overall, with this model, I was able to work from genes to metapopulation scale and to look at the consequences of dispersal both at demographic, phenotypic, and genotypic levels. So I was interested by looking at different outcomes. For example, to look at the evolutionary dynamics of populations, I looked at the temporal evolution of the phenotypic or genotypic traits over 50 years, and I was also able to differentiate between immigrants and philopatric patterns. I was also able to look at the temporal evolution of the population abundance, so the demography, and to summarize patterns at the metapopulation scale and to be able to compare scenarios, I used the five last years of different metrics. So now we can move to the main chapters of my PhD. So as I mentioned earlier, dispersal is overlooked, and especially its implications in the case of salmonids. So my first objective was to demonstrate potential implications for the stability and the evolutionary dynamics of populations. So I first adopted a parsimonious approach by focusing on the relationship between dispersal and network stability, so without diversity among populations. So I simulated a network with a realistic spatial configuration based on Brittany, with homogeneous populations at initialization, so they have the same environmental conditions and the same distribution of traits at the beginning of simulations. And I simulated a gradient of dispersal rates from 0 to 50%. So first, I looked at the consequences on the demography of populations. Here you can see the source sink dynamics of the network. You can see asymmetric flows between populations, represented by the arrows. And you can also see that there are different types of populations, source, neutral, and sink, based on the ratio between the number of immigrants and emigrants. Then I looked at the stability of the network, measured by the porphyry effect metric. So with this metric, if the porphyry effect is equal to 1, it means that the stability of the network is like if it was a big unique population. If the porphyry effect is above 1, it means that the network is more stable than expected. So we observed this nonlinear relationship between the stability of the network and dispersal rates, which can be broken down in 3 different steps. So first, without dispersal, we can see that the stability of the network is above 1, so which means the network is stable. Indeed, population dynamics are asynchronous, they are independent, which favors the stability of the network. However, if we look at some small populations, there is still some risk of extinction due to the demographic stochasticity. That's why then, for dispersal rates of 10–20%, we have an increase of the stability of the network. And this is explained by the demographic rescue of these small populations provided by immigration. And then, for dispersal rates above 20%, we have a decrease of the stability of the network, which is related to the synchronization of population dynamics due to dispersal. So overall, we have this nonlinear relationship suggesting that there may be an optimum of dispersal rates for stability around 10–20%. This may be context dependent, but still it's interestingly close to the average immigration rates that are measured in the wild populations. Then I looked at the phenotypic and genotypic consequences of dispersal. Here you can see the proportion of 1C winter individuals in returns. So this reflects the maturation strategy at sea as function of dispersal rates and the different types of populations, sink, neutral, and source. So we can see contrasted patterns between populations. In the sink populations, we have a decrease of the proportion of 1C winter individuals, which means the maturation at sea is later. Whereas in the source populations, we have an increase of this proportion with increasing dispersal, which means the maturation is earlier. And these changes can be explained by two hypotheses. When looking at how we represented the maturation strategy, it can be due to genetic adaptation of the maturation threshold or plastic response to the environment. First, we looked at the maturation threshold, and it doesn't change with increasing dispersal, so there is no genetic adaptation. However, we did observe plastic response of individuals to increasing dispersal. Here you can see the same pattern of small size, which decreases with dispersal in sink populations and increases in source populations. And these changes are related to density-dependent growth, since in sink populations, density is increased with immigration, whereas in source population, density is relaxed when there is a lot of immigrants. So overall, we observed this phenotypic diversity among populations emerging from plastic response to density changes induced by dispersal. So in this first part, I was able to show the implications of dispersal for the stability and the evolutionary dynamics of populations, but it was dispersal alone. And so then I was interested by the potential interplay between dispersal and diversity among populations. So there is a large body of literature exploring this interplay between dispersal and diversity. However, most of the time, they are in the context of divergent selection, so they show that dispersal or gene flow is limiting adaptation of populations. But in the context of changing environments or maladapted populations, dispersal and gene flow can also benefit to the adaptation of populations. Moreover, these studies are often using a simple spatial structure with symmetrical flows between populations. And so we can wonder if a more complex spatial structure with asymmetric flows could influence this interplay between dispersal and diversity. So in this second chapter, I evaluated the adaptive capacity of both adapted and maladapted populations with the case of a more complex spatial structure of populations. To do so, again, I used MetaIBASM to run different scenarios. I worked with a simple spatial configuration with the same distance and the same carrying capacities between populations. Populations were maladapted at the beginning of the simulation, because I shifted their distribution of traits from the emerging optimum, for example here, of the graph potential, and I compared different scenarios of spatial structure of genetic diversity. For example, I compared this scenario, so without diversity among populations, they have the same distribution, with the second one, where there is diversity among populations. They have different distributions, and here they are gradually ordered across the network. And I compared with the third scenario too, with in this case, a random distribution of diversity across the network. So to be able to compare these different scenarios, I shifted the distribution of traits of populations with the same distance on average from the optimum to be able to compare them, and that was not the case in my manuscripts. And I simulated these scenarios for gradient of dispersal rates. So we can look at the results at the local scale. So by focusing on some example of populations, here you can see the evolution, the temporal evolution of the growth potential in one population over time, within philopatric individuals and within immigrants individuals, which represents the contribution of immigration to the population. So we can start with this scenario without diversity among the network, and we can see that at the beginning of simulations, the population is maladapted. Its growth potential average is far from the optimum, which is represented by the dashed line. And over time, the population is evolving towards the optimum. And the pattern is the same within immigrants individuals. However, in the scenario of gradual distribution of diversity, the population is evolving faster towards the optimum and even faster with high dispersal rates. And this is related to the immigration patterns that are closer to the optimum. Then in the last scenario with a random structure of diversity, the population is evolving even faster. And this is again related to the immigration, which provides more opportunities for adaptation to the population. We have some variability of patterns between populations. For example, in this population, we have more contrasted differences between scenarios. But on average, the final local tree mismatch of populations is lower in the case, in the scenario where diversity is combined to dispersal. And this has positive consequences on the metapopulation size. So here, I was able to demonstrate that dispersal and genetic diversity among populations favored the adaptation of population via this evolutionary rescue effect. And this supports the adaptation network theory that I was talking about earlier. And we went further by showing the influence of the spatial structure of this diversity across the network, since the random distribution of diversity showed higher adaptation of populations and higher metapopulation size. So then I went further by exploring the influence of the spatial configuration of populations. I used this same scenario of random distribution of diversity, and I compared different spatial configurations of populations. Here, with the same distance and the same carrying capacities between populations, the second one with variation of the distance between populations, and the third one with variations of the carrying capacities. And again, populations started simulations maladapted, and I simulated a gradient of dispersal rates. So again, we can look at what happens at the population scale by focusing on some example of populations. Here, the population 10, and here the population 1. So with a simple spatial configuration, again, we have this evolution of populations towards the optimum. But when we simulate a network with distance variations between populations, we can see that the evolutionary trajectories of populations are modified. In this one, it's quite similar to the first scenario, but in this one, the evolution is fostered by this scenario of distance variations. And again, this is related to immigration. And in the second scenario of carrying capacities variations, again, the trajectories are modulated by this scenario. Here we can see an increased adaptation of the population, whereas here the population adaptation is limited. And so we have opposite patterns as function of populations. Again, this had consequences on the demography of populations. And so overall, we showed that a more complex spatial configuration with asymmetric flows between populations can modulate the evolutionary trajectories of populations. And we also highlighted this dependence on the local context, which populations are surrounding which populations. And so these results also suggested that a better knowledge of the asymmetry of dispersal patterns could help to better understand populations' evolution and their management. That's why in the last part of my PhD, I evaluated management strategies that consider this metapopulation structure and that conciliate both conservation and exploitation. So there are some studies that warn that we should consider the metapopulation structure, but there are only a few that explicitly compare different strategies, and especially considering an evolutionary perspective. Yet, in the different parts of my PhD, I could show that dispersal could influence the demography of populations, but also the evolution of traits. And exploitation can also influence the demography of populations, the evolution of traits, via what we call fisheries-induced evolution. So this suggests that we should evaluate management strategies within this integrative framework. And that's what I try to do with this last chapter. So more specifically, I compared 3 different scenarios. The first one with exploitation applied on all populations. The second one with exploitation applied only on sink and neutral populations, so conserving the source. And the last one applying exploitation only on source populations. So I simulated these 3 different scenarios with a gradient of local exploitation rates and a gradient of dispersal rates. And to be able to compare these different scenarios, I computed the metapopulation exploitation rate, so I was able to compare for the same metapopulation exploitation rate and for different local exploitation rates. Sorry. So I first looked at the demographic consequences by looking at the abundance of the metapopulation as function of increasing exploitation. So first, with the scenario of exploitation applied on all populations, without dispersal, we have a decrease of the metapopulation size with increasing this exploitation. And the pattern is the same regardless dispersal rates. However, when looking at the different management strategies, with the conservation of source populations in blue, we have a slightly higher metapopulation size for low exploitation, but a lower metapopulation size for higher exploitation than 50%. And this pattern is different as function of dispersal rates. Here, for example, for a dispersal rate of 30%, we have a higher metapopulation size for a larger range of exploitation. However, the scenario of source exploitation show lower metapopulation size, whatever the exploitation rate and whatever the dispersal rates. So overall, I showed variable metapopulation size depending on our different management strategies, but also depending on exploitation rate and dispersal rates, all of this interacting. And this results of a slight higher benefit of conserving the source populations while exploiting the sink and neutral is quite counterintuitive when managers could think that it should be better to protect the small endangered populations. And in this work, we show that considering dispersal and the benefit from immigration to compensate the exploitation can lead to different results. And then I was also interested by the phenotypic and genotypic consequences of our scenarios. And so I showed we can look at the growth potential evolution as function of the exploitation rate. Here, starting with the exploitation of all populations. So we can see a decrease of the overall growth potential with increasing exploitation, which can suggest selection against high growth individuals, and so fisheries-induced evolution. However, looking at the size of juveniles, the size increases with exploitation, which can be rather due to plastic response to density, which is relaxed when there is exploitation. And when we look at our different management strategies, we can see that the results are even more complex with some interaction between exploitation and dispersal rates. So we think that these different results are a combination between local selective effects, density effects, and immigration dilution, but we have to go further into the results to be able to explain them. And so this will be done by looking at the population scale, comparing the exploited and non-exploited populations. Sorry. So my work was the first exploration of this framework of adaptation network in the case of salmonids. And in the first chapter, I was able to show the effects of dispersal alone. So first, demographic rescue effect of dispersal on small populations, but also its synchronizing effect on population dynamics. I was also able to show genetic rescue effects that I didn't mention in this talk, and phenotypic diversity among populations emerging from plastic response to density. Then I evaluated in the second chapter the interplay between dispersal and biocomplexity, and I was able to show this evolutionary rescue effect of dispersal on maladapted populations. I also didn't mention in this talk, but I showed that this evolutionary rescue effect was largely dependent on the reproductive success of immigrants. And I had a focus on the influence of the spatial structure of populations on this evolutionary rescue effect. And finally, in the last chapter, I demonstrated the effects of different management strategies of exploitation on both the demography via compensatory effects, but also on the biocomplexity of the network with some evolutionary and plastic response of populations to exploitation. So we can get several messages from these results, and especially on the implications of metapopulation structure for the management of salmonids. So first, that populations cannot be considered as isolated, since we showed in the different chapters that what happens in one population can have both demographic and evolutionary consequences on connected populations and vice versa. I would also suggest that eco-evolutionary dynamics of metapopulations cannot be ignored, since dispersal can play on this loop between the demography and the evolution of traits. Then I think my results encourage getting more knowledge about metapopulation structure, and especially about dispersal patterns, since we showed that they may drive populations dynamics. And finally, I think my work suggests the benefit of conservation of adaptation networks. This topic is more and more appreciated in other organisms, such as corals, but I think it could be applied in the case of salmonids. So regarding the modeling approach, I was able to demonstrate the implications of dispersal by using a modeling approach which integrates the complexity of the life cycle, evolutionary processes, and also metapopulation structure, all of this in the single framework. And this is the first model which integrates such complexity in the case of Atlantic salmon. But because it is based on the configuration of Brittany, it doesn't mean that my results are predictions of what happens in these populations. First, because we don't have enough data to compare our results to what is observed in Brittany, and also because that was not the objective of my PhD. The objective was rather to explore different scenarios, to get some lessons, and to identify gap of knowledge. So I think this approach was here used as a prospective tool rather than a predictive tool. However, one objective of the model is to become applicable on different rivers from Europe, for example, because they have different spatial structures or different environmental conditions. But the current version of the model is not enough flexible to be able to represent, for example, different spatial structures. And so this led us and me to develop a new version of the model. And this took a significant part of my PhD. The model is still under progress, but I think we could use it to explore several potential ideas, such as the causes of dispersal. In my PhD, I focused on the consequences of dispersal, but the causes also deserve attention, I think. In this work, I simulated a dispersal rate which was constant in space and time and which was random, not based on individual features. However, there is a large body of literature showing that dispersal mechanisms might be more complex, and dispersal might depend on the phenotypes or the context of the population. We still don't have a lot of information in the case of salmonids, but still it could be interesting to explore more complex mechanisms of dispersal, and especially a genetic basis. We could explore if implementing a genetic basis of dispersal could lead to the emergence of different dispersal rates as function of, for example, the configuration of the network. We could imagine that within a homogeneous network, dispersal rates could emerge around 20%, as suggested by my first results in the first chapter. In a heterogeneous network, we could rather expect more variation in the dispersal rates between populations and also in time. With the case of exploitation, we could expect fisheries-induced dispersal evolution. For example, we could imagine that applying exploitation on sink populations will select against dispersal in source and for dispersal in sink. So there will be these flows of individuals leaving the sink populations, and so we would no longer have this rescue effect from source populations. In the case of climate change also, it could be interesting to evaluate if dispersal could be selected as a strategy to face climate change or counter-selected due to its synchronizing effect, since climate change may synchronize environmental conditions between populations. And finally, my work was the first exploration of this framework, but in a quite simple case, with environmental conditions that were constant, and we could evaluate this framework with changing environmental conditions, such as in the case of climate change, and evaluating if dispersal and diversity would provide opportunities for salmon to adapt to climate change. So I would like to thank you all for your attention, for being here. I would like to thank the fundings, my supervisors. So Mathieu, merci pour tout. Stéphanie, I was very lucky to have you in my supervision, and thank you for your help in my housing adventures. Étienne, merci pour ton investissement pendant ces 3 ans. C'était vraiment bénéfique à ma thèse. J'aimerais aussi remercier tout le labo EcoBiop, l'UAR, Numéa, l'UMT pour tous ces bons moments partagés au sein du labo et en dehors. Mes copains, donc Marius, Dorida, Léa, sans qui la thèse n'aurait pas été la même. Et les copains de la danse et du rugby qui me rappellent tous les jours qu'il n'y a pas que la thèse dans la vie. Et ma famille est écotique. Merci.
Thank you, Amaya. perfectly timed. Well done. Now it's time if someone needs to leave the room. It's a good opportunity now. And then we will start with comments and questions from the jury. And I think first one out will be Marie. That's fine with you. So the floor is yours.
Yes.
Yes.
Findings and the discussion of that. Maybe a bit too much sometimes. It have been difficult sometimes to find my way through all these details. But here today with a presentation in maybe a more constrained structure, you've been really good at highlighting the key messages, and really I would like to congratulate you on that. You've shown also a great expertise in both the theoretical aspects of the work you've been involved in, and also a very skillful modeling work. And again, congratulations about that. Maybe as a first word, I'm coming from, have been starting ecology from a bird and mammal perspective. So when I switched to salmon, I've been very surprised to understand and to learn that salmon were not dispersing, contrary to many of the vertebrates. And you present this very nicely in your introduction, and I could really recognize myself in that, saying, where are there just some deviant individual doing some straying and not really proper dispersal? So thank you, Amaya. Thank you very much for bringing back the dispersal into the life cycle of salmon as something rather normal. I really appreciate that. Maybe I can go through the first question now. And in your setting, in the life cycle of the salmon, in particular, the dispersal here is not around, how to say, doesn't happen just the individual can disperse whenever they want. Here in this case, dispersal is strongly conditioned on the migration decision, and this being strongly dependent on the smoltification process by which salmon will be able to adapt to a small regulation condition in the sea, from the river to the sea. And I wonder to what extent this specific system, which is a salmon, may differ or change the way we consider, or theoretical studies consider, dispersal in, say, birds and mammals.
Yeah, I understand your question. It's true that the case of salmon is very specific to dispersal regarding this. We could imagine, like in, for example, in dendritic structures with different populations in the same estuary, that maybe there could be dispersal, for example, of juveniles between populations. But in my case, with this structure of different rivers across the coast, it is very dependent on this smoltification decision and migration to the sea. But clearly it's different than other species that don't have this anadromous strategy, and for which dispersal could happen in the life cycle at maybe any stage. So this is very specific to the case of anadromous species, and this will imply differences in the way we represent the dispersal process. For here, dispersal is related to smoltification.
But so in your model at the moment, do you think that there is something specific that accounts for this smoltification process that comes first, that condition dispersal? Or do you think of any way to include it, to make it more realistic, given this anadromic in salmonids?
I'm not sure to get your question.
Okay, well, never mind. I will switch to the next one.
Okay.
In your system and in your study, you've put a lot of emphasis on dispersal in this metapopulation context, and you nicely show, as you can see here in this summary slide also, that dispersal is a synchrony. It can increase synchrony between nearby populations by this flow of individuals between one population to another. But again, in the case of migratory species like the salmon, where salmon from individuals from different populations gather at sea for maybe half of their life cycle, how do you think dispersal and common feeding ground may really contribute each other to this synchrony? This is not something you've been considering explicitly, I think, in your manuscript, and which I was wondering about.
Yeah, that's a very good question. I really think that these common marine conditions could synchronize population dynamics. In the model, the marine area is the same, but we can randomly pick the daily marine conditions for each population, so we can control this covariation of conditions. In my work, this random pickup of conditions was independent between populations, so we didn't have this potential synchronizing effect of marine area. But I was also interested by this question of relative influence of dispersal and environment on the synchrony. And so I did some simulations, but testing the influence of river conditions covariations. And with these river conditions, I showed that dispersal had a very relative minor effect compared to the environmental conditions. So I would think that the marine conditions would also have a strong synchronizing effect compared to dispersal.
Okay, it's interesting. Very good to know. Thank you. Just for a change, a small question about one of the hypotheses you've put in your model. You said that dispersal is modeled with 80% of the dispersers traveling less than 50 kilometers. And again, I thought it was very limited compared to the swimming ability of the salmon that can swim up to Greenland. How do you justify this choice here?
Yeah, so this choice was based on the few literature on dispersal in salmon. I think it was based on one paper from the Imsa River in Norway, and also the review of Kiefer and Kodir. And so they measured that a large proportion, 80% of individuals, were dispersing less than 50 kilometers. But it still allows some long-distance dispersal, but I think the hypothesis behind these results is that even if they have strong swimming abilities, they still are influenced by the chemical odors of their natal rivers. So I think that if dispersal occurs, it is still close to the natal river. That's the hypotheses that are coming, but we still don't have a lot of data. But this might be possible, long-distance dispersal.
Okay. One thing I really enjoyed in your work and in your modeling framework is this eco-evolutionary approach with some parameters like fitness, for instance, really being an emerging property of the model, like a byproduct of the model, not really something fixed put in the model. And I think it's very neat and clever way to to investigate such a questions here. And I was wondering also if, it's very naive probably question, sorry, but if at some point we could also have the dispersal rate as this kind of an emerging property of the model, by which we could see how this dispersal rate may evolve by itself, and how this would fit or not to the 20% optimum, like best compromise that you highlight in your model.
Yeah, exactly. That's why I tried to explain at the end of my talk that I think it's a very interesting area to study. So in my PhD, we adopted a parsimonious approach by fixing dispersal rates. This allowed us to better understand metapopulation functioning and everything. But for sure, putting a genetic basis of dispersal will allow us to study dispersal as an emerging result from the model. And so, I totally agree that this is an interesting area of study.
And do you have some ideas, some guess of what would happen in this case?
I would think that in the case of a homogeneous network, dispersal rates might emerge around 10-20%. That's in the case of more diversity among populations, maybe local adaptation. We might observe more variations in the dispersal rates emerging, more variations between populations, but also in time. And as I said, with exploitation, we could also see interesting response of dispersal to exploitation. Yeah, this kind of hypothesis.
Okay, thank you. Then I had another question about this later part of your work, trying to link this eco-evolutionary dynamics and modeling with the management and exploitation of this population. I think crossing this bridge here is really interesting and illuminating also in the way we consider evolution and the management of this population. And I take good note of your results saying that the exploitation of source population is probably not a good idea at all. But I was wondering to what extent the proportion of source and sink population in your metapopulation would influence these results. I mean, if you've got a very high number of source population or sink population, could you better spread the efforts between those and the exploitation of source population being less dramatic in this case? What do you think? You see, my question is about the proportion of source and sink population within the metapopulation. How would this potentially affect the output you've been providing here?
Yeah, I think it could affect our results, but I have to admit that I have no idea of how. I would imagine that if we have more source populations, so less sink and neutral, if we still apply the same exploitation rate on this sink and neutral, the exploitation rates will be very high locally, and so this will probably affect the extinction risk of these small populations. But we would have a large number of source populations that might provide rescue effects. So I don't know, what will be the compensation between exploitation and immigration. I think this is really something that we should test about regarding this chapter. Yes.
Okay. And you've been considering management actions through the management of fishery alone. And I was wondering if you could think of other way to act on the management of this metapopulation through, I don't know, dam management or removal or some stocking. Do you think of any way that might be more effective maybe than just managing the exploitation rate?
Yes,
given what you know now about the functioning of the dynamic
at the beginning I was wondering if I should even compare management strategies of exploitation with management strategies of, for example, rivers carrying capacities. So I had some ideas such as increasing the carrying capacity of the river. For example, we can imagine that we improve the habitat and the spawning grounds, so the carrying capacity is higher. We can also imagine that this could reflect, as you said, dam removal, so access to new spawning grounds. So yeah, I think we could also explore this. And my hypothesis would be that, again, improving the habitat of source populations, for example, could lead to more rescue effects. So some hypotheses like this could be tested, for sure.
Yeah, many more studies.
Yeah, many more.
Okay, it's a great tool indeed to investigate such a thing. But when coming to the end of your manuscript and a little bit here also in your oral presentation, I've been very surprised to see how much you've been criticizing your work and your modeling, and why so much doubt really about your work and the limitation of this. So I was a bit surprised, and I say, what do you think would be the way forward? Is it increasing the complexity, how to make it more general at the same time? How do you see this today?
Yeah, this question of generality of my results was quite prepondering. I don't know if it's an English word, during my PhD. And I think that showing some, identifying some important features of, for example, the network, such as the spatial structure, led me to ask, okay, so are my results generalistic regarding this spatial structure? Because I used only one type of spatial structure. So, for example, I think for more generalism, I should test different spatial structures. For example, with different source populations located in another area of the network with some dendritic configuration of rivers. Again, when I showed that dispersal patterns were really important for the dynamics of population, I was wondering, are my results generalistic? So again, I think that we should test different dispersal mechanisms and look if the lessons we can get are still the same. So yeah, I was quite criticizing the generality of my results, but I think we have to test different scenarios of the points we really identified as important to be able to be generalistic.
So I see it's been kind of a longing question, a question hanging in your head all the time, maybe a bit of a burden also to carry over the PhD. So what would be your advice for a young student starting a PhD with such a kind of modeling?
I would say that we cannot test everything at first, that we have to process like step by step. First, exploring one hypothesis, and we have to make a compromise, trade-off regarding some hypotheses. We cannot directly apply a complex mechanisms of something. So first we start simple, and then we try to increase progressively the complexity with the results we can get, and just be patient. And yeah.
Okay, good. I'll try to keep this in mind for myself too. And maybe just a last question is about one of the perspectives you present today in the oral presentation, but also in the manuscript. You say that you would like probably to apply this modeling approach to other species or other population or metapopulation systems, and for instance to salmon, to Pacific salmon in California. So I was wondering really what characteristics of those population or those species are so different that you would want or need to run the model or to adapt the model to those specific things. I mean, is there any specific characteristics that make them so different from the Atlantic salmon that you really need to run the word process instead of transferring the results from the knowledge you gain from this modeling on the Atlantic salmon?
Yeah, the idea is, as you said at the end, is also to apply the same ideas. So, for example, I was considering that the Pacific salmon in California has like this same situation, being at the south of the distribution range, being threatened by climate change, for example. But in terms of differences, I think it will be mainly in the life history strategies or life cycle. Also the spatial structures of rivers, but I agree that we could also have different spatial structures within the same species, for example, for Atlantic salmon, between Brittany and the Adour system, for example. So these perspectives were more like enlarging my results to other species, but there may be differences, for example, in the life cycle, I would expect, but I don't know if it would really change the results.
I think it's really nice, again, always to find a way to compare different systems and different populations. But I was wondering whether it would really bring something new that you can't predict yet from what you've learned with your case study.
Yeah, I don't know.
Okay, thank you. I think I will leave the floor to the other reviewers. Thank you very much, Amaya.
Thank you, Marie.
Thank you, Marie. Then I think it's Nicolas.
Thanks. Well, let me first say that I'm so sorry I could not come to Pays Basque to meet you in person, discuss that, see the nice country, but well, my teaching load this week has made that impossible. Maybe another time. Then I'd like also to repeat Marie's congratulations to you, Amaya, about the quality of the work, the quantity too. Even in electronic form, I can see the how heavy it is. So, and sometimes what's quite a struggle to understand and to go deep into the complexity. But it's really an excellent thesis. I think you can be proud of, and the fact that you constantly doubt about your results. Well, you can say you doubt about results. We can also say that you perceive the limit of your work. This is the DNA of scientists. We should not go too much into that. But I think, in my view, this is really an important point, and I think that's good to use this this reflexive thinking on your work. Let me come back to a few questions, and I think, as Marie said, she comes from a bird and mammal background. I have a butterfly background, also a terrestrial background. So you'll see that some are connected. And well, sorry if I do the devil's advocate on some point. So this is not to make you doubt more about your results, but just to see, with an external eye, because my excursion to salmon was very short, how this make me see your results a bit differently. So you said in your sometime in your presentation that your model is based on simplifying assumptions. Well, that's normal for models, and especially on dispersal. And I see two main differences between salmon and many terrestrial species about dispersal. Do you see the same as I do? So what would be, yeah?
I would say the first one is what we talked about with Marie, about this condition on the anadromy strategy. So I would say dispersal could happen regardless some strategies in other organisms. And the second one...
the second one, the second one is that, so yeah, the first one is it's an anadromous species. So dispersal is intimately linked to migration. Okay? And the second one is that it's dispersal in a dendritic system. And for me, this makes major difference compared to terrestrial species, but still some of your assumptions or some of the discussions sometimes are based on knowledge accumulated on well, I say terrestrial species, but at least species that would disperse independently of migration and that would disperse as the crow flies. And then I'd like I'd like your view on what makes the salmon different in terms, for example, of on connectivity, on dispersal costs, on the fact that dispersal is three steps, I mean, three phase process. So, for example, I mean, let's start by something. What cost of dispersal do you expect in a salmon?
Yeah, so regarding the cost, it is true that we don't have this cost of migration and transfer that we could have in other species, where either we disperse or not. For salmon, for the anadromy, they will migrate anyway, so it is true that for dispersal, there is no this cost of migration, I would say. Maybe just a little cost of a longer migration to reach long distance rivers, for example. But I would
or a short one.
Or a short, or a shorter one. That's true.
So you could even say, I mean, if you could even say, and I like Marie's work about straying, because when I went into the salmon world, that was really astonishing to me how dispersal was perceived negatively, contrary to the whole rest of ecological where dispersal is good. So just a salmon that takes the wrong river, let's call it the wrong river, okay, by migrating upstream, whether it's a choice or not. Well, I have some problems in seeing the cost, and especially to believe that the cost and then the likelihood to do so can be linked to distance. But in your model, you assume, for example, connectivity linked to distance. There, I don't remember which page, but you have a matrix, okay, of dispersal. How reasonable is it is for a species that is anadromous?
Yeah, I think it's just the distance, because it may be farther from the natal river, but otherwise, like for example, within, as you say, the dendritic system, this distance effect might be very low. Yeah. Yeah, this can ask the question about the dispersal kernel we used, but we based it on some results that came out on salmon. But yeah, it's true that the cost may be strongly related to, like for example, not finding a good habitat to spawn or limited reproductive success. But it's true that this cost of migration related to distance might be lower compared to other organisms.
I think that maybe not for you. I mean, I don't know what's the next step of your career, if you're going to continue on that, or for the next PhD student. But I think that trying alternative models where dispersal is the probability of dispersal, with, for example, simply depend on the number of river split between two different populations, assuming that each time a fish comes to a choice, should I go left or right, knowing that, because they somehow perceive that homing is going, let's say, left, okay? The number of times there's this choice. I would be curious to see if they would change the result or not. And then maybe a smaller one, but still linked to dispersal. You mentioned somehow, I don't remember where, you mentioned a bit in the introduction that there could be dispersal in time, which is something which is particularly fascinating for some species. But how really is it the case for Atlantic salmon?
Yeah, I think it's the case, and it's included in the model with the different alternative strategies. For example, for the same cohort of individuals, some will stay, let's say, 1 year in river or 2 years in rivers. Then some will migrate to the sea. Some will stay in river as spawning pars.
But is it dispersal? Sorry to interrupt you, but is it dispersal? Is this dispersal? So if some fish come back after 2 years, some after 3 years,
yep.
but they come back to the same population, this is not dispersal in my definition.
To me, it's temporal dispersal, not spatial dispersal, but temporal.
For me, it's not temporal. What is the definition of dispersal? Let's go back to the beginnings.
I think dispersal is the fact that the individual will not reproduce with the same population. So this could be a definition in space, but in time it could be reproducing with the related individuals, like the same cohort.
Sure, but then why? If you have some variation in the age at maturity, okay, then there will basically be at every reproduction season, there will be a mix of individuals with different age.
Yeah.
This is absolutely no different from a population of birds, mammals, butterflies, whatever, that do not have a yearly year cycle, okay, and live at the same time, at the same place. So this, for me, is no dispersal. So, okay, just dispersal is defined as some individual that is going to reproduce in a different population that it's population where it's born. It can be in space, that's easier, okay?
Yeah.
In time, too, but then there must be two different populations at the same place. And this is the meaning of my question, because for me, this is the case where I don't recall which species of Pacific salmon, but that have a very
the pink salmon.
Small variance. So basically they have an age at maturity of 2 years.
Yeah.
So basically in the same rivers, you have two populations. You have the odd years populations and the even year populations. And in that case, a salmon going back after 1 year or 3 years will change population. But if you have a larger variation, that there is anyway a mixing every year, then you don't have two populations at the same spot. You simply have a variation in age and maturity, as you have in many populations that stay in the same place, whether or not they migrate. So I think this dispersal in time is fascinating, but it may not be the case in Atlantic salmon if you have basically too much mixture. You see what I mean?
I see what you mean.
Okay. Then something else that I found fascinating on salmon is the extremely high fecundity they can have. What is, in your opinion, the impact of this huge fecundity on the individual reproductive success, but moreover on dispersal evolution and metapopulation dynamics? So to precise my question, I mean, compared to many species, the variance in reproductive success in salmon is much higher. How then this makes it different for dispersal evolution and its impact on metapopulation dynamics for you?
So you mean the reproductive success might be very variable because the fecundity is very high?
Yeah, and I'm speaking especially, for example, for colonization. So you can have a new population, I mean, a new habitat colonized by a very tiny number of individuals and really rapidly go to carrying capacity.
Go very fast, yeah.
Well, if you look at a bird, maybe some will have 5 youngs, some 6, but none will have 1,000. While in salmon, you can have a huge variation like that. So does this make the situation different for metapopulation dynamics and dispersal evolution?
Yeah, it's true that in the case of colonization, we can imagine that the colonization will be very fast, but in the case of not colonization and just flows of individuals between populations, I I don't know in which way it could go, but yeah, it might influence the speed of evolution of traits. Yeah, I didn't think about that. In my case, in my simulations, I saw a quite fast evolution of traits within only 20 generations. So I would say this might be due to this high fecundity compared to other species, but yeah, it would be interesting to compare this case of lower fecundity.
I don't have the answer, but I think it makes the case quite different also for genetic structure, because you can have populations that are very, very young with basically very small genetic variation because they are the product of a very few individuals. While for species where the fecundity is lower, you will need a longer time and more variation to get up to big population. Let's go to two more specific questions. You mentioned in your thesis, and I quote, the larger the population, the more attractive they are to dispersing individuals.
Yeah.
I wonder if you have any idea what could be the mechanisms. So for example, is it known whether salmon could, I would say, explore different population before deciding? It's known in several species that basically will sample different habitat patch and say, well, this one seems best, I'll settle here.
So there are different hypotheses about that. First, there is, if I remember well, a hypothesis regarding the river flow, which could attract salmons. So a larger river could have a larger river flow, attracting the salmon. Then there is also an hypothesis regarding collective navigation. So this hypothesis means that at sea and then when they come back to the river, individuals will form some groups, some collectives, and so individuals will be attracted by a larger group coming back to a larger river, the individuals that are homing to their river. So this is an hypothesis that could explain why they will be more attracted by large rivers. And there is also an hypothesis regarding chemical attraction from congeners, from the pheromones. And so this hypothesis also could explain why they are coming back to larger rivers with potentially more density of individuals. And the hypothesis of exploration is also a good one. There are some studies also on other species showing this exploration behavior, at least in the first kilometers of the rivers. That could also be an explanation of this attraction to larger rivers.
Yeah, I think that the second mechanism you mentioned is fascinating, because group dispersal can make a big difference into connectivity and then metapopulation dynamics. Because basically even if in the salmon, because of the fecundity, I said it maybe will have a lower effect than in other species, but it's quite fascinating. Then let me go to a quite technical question and a bit really devil's advocate. Maybe you can put back the slide 59 of your presentation if it's not too hard, so that the audience can also see. It's where you basically show the impact of the dispersal rate on the portfolio effect, and you conclude that basically there is an optimum.
Yeah.
It's 59, it's 60, it's on several slides. Yeah, okay, that one. Yeah, okay. Well, I could say, given the huge variance you have, I do see a flat line. I do not see any result, basically.
Yeah, the bars are based on our different simulations, so 100 simulations, and it's quite conservative. because it's the quantiles 95%. So if we look, for example, at the larger error bars that are 50% quantiles, yeah, the bars are smaller. It's quite difficult to analyze results from simulation because I don't know like specific tools to statistically differentiate the scenarios, because it's based on simulations, so we choose the parameters and everything. So I'm not sure if we can use statistical differences. But in my opinion, there is a trend, which is not flat. But
I agree with you. I agree with you, and I think that you pinpointed the problems. Well, there are statistical tools. You can analyze this with any statistical tool you want. The problem will be what is that everything is going to become significant if you have enough statistical power. So if it's not significant, just double your simulation run and it's becoming significant. So I agree with you. It's hard to know. To know where basically the truth is, but okay, it was a bit a provoking question. Maybe maybe a last one. You said in your discussion or conclusion, at least you advocate that we should acquire better information on spatial structure and dispersal for salmon.
Mm-hmm.
Do you have any advice on which method you could apply, knowing that I don't know if it's the same in for Atlantic salmon, but for the Pacific salmon, there is money. I mean, it's such a huge industry, so that if you frame it correctly in a business way, you could acquire a huge amount of data. So it would be feasible. But what would you advise to do to collect more information on spatial structure and dispersal?
So I will tag all individuals and put antenna everywhere.
Okay, I said there was money, but maybe not infinite. But still, okay.
No, yeah, I think this system of tagging an antenna is the best way to know the dispersal patterns. But then we still miss this information about reproductive success. So I would say we still have to combine these techniques with also genetic studies, where we can reconstruct the reproductive success of dispersing individuals. Genetic tools, without the tagging system, genetic tools can also help to identify immigrants within a river. So within a river, we could know the proportion of immigrants, but genetic studies are also expensive. So I don't know if there is a magic technique to better know the patterns, but a combination, I think, of tagging and genetic studies would provide the best view of what happens between rivers.
At what age can you tag them, or what age or size or whatever?
Oh, we can tag them very early, like at the power stage. And for example, if you because there are some monitoring, for example, on rivers, they are tagging the individuals, and then if we put antenna on other rivers, we can know if these individuals went to other rivers. We could also just compare like the proportion of tagged juveniles and the proportion of tagged returning adults, which could help to know which proportion emigrated to other rivers. Yeah, this kind of.
Yeah, but importantly, you can tag them before they they migrate downward to sea. Otherwise, it's pointless.
Yeah.
Okay, thank you, Amaya, and congratulations again. It was really a pleasure to see a thesis. And the last word, I did not tell it, but I think the presentation of your thesis, it makes it really smooth and really nice to read. And I want to congratulate you on that too.
Thank you.
Thank you. Then we will move to Will.
Yes, thank you. You hear me okay?
Yes.
Yes. Great. And so first, I just want to echo the sort of congratulations and thanks from both of the earlier reviewers. I think it's really impressive amount of work you've done. Really well presented, and I also really appreciated the the presentation today. Really helped sort of as people mentioned, there's quite a bit of material, and so it really sort of helped me see how it sort of all fit together. And so there are a few questions that were brought up earlier that I'd like to sort of build on a little bit, and I have a few questions of my own. Although I also have to say, the reviewers did a really good job of hitting on most of the questions I would have asked. But one sort of interesting commonality, and I also have a background sort of before I started working on salmon in a terrestrial system, but in my case, in plants. And so I'm actually going to push back a little bit on this idea that it's really unique that sort of dispersal is limited to this one phase in the life cycle for salmon. Do you see any parallels to when in the life cycle plants can disperse? And is there sort of anything you can learn or contribute to the literature in terms of people who've been studying dispersal in the context of plant populations?
You mean if like there is something specific in the life cycle of plants regarding dispersal?
Yeah, I mean, in the sense that a plant really its only chance to disperse is at the seed stage.
Yeah.
And that's essentially sessile the rest of its life. And I mean, even more sessile than at least juvenile salmon can move around the stream to some extent. But I was wondering, is there anything?
The dispersal is limited to reproduction, like the seed steps of reproduction in plants, whereas dispersal can be before reproduction in salmons.
Right. I was wondering if you've had a chance to look into any of the plant literature and how that might complement what you've been doing.
No, I have to admit that I only looked on animal dispersal. Yeah.
Yep. Which is fair enough, but yeah, I think it could be worth thinking about. And then let's see another, well, so there were questions brought up about, sort of what, if anything, would need to be different in the model to apply to Pacific salmon. And so I have a few thoughts and questions there, which I'll probably mostly save for later to sort of circle back to after we have some discussion that's more, focused on the work you did. But one sort of biological difference that right off the bat does occur to me is that the Pacific salmon we're interested in, with the exception of steelhead, which some people argue is a trout, not a salmon, those are all semelparous compared to Atlantic salmon, not necessarily having a very high rate of repeat reproduction, but at least in theory being iteroparous, which then that also sort of, well, so one, do you think iteroparity had much effect on any of the outcomes you saw in your model? But then also, do you think there could be any consequences to or any differences in the dispersal behavior of salmon of Atlantic salmon on sort of their first trip to the ocean versus later trips?
So yeah, as you said, iteroparity represents only a few proportion of individuals, but if we could imagine that at their first reproduction, for example, they already disperse, so they will provide their genes to this population, and then in the second one, they could have the kind of the choice between coming back to their natal river or this second river or even third population. So this could have, I think, consequences by increasing the potential influence of dispersal between populations. But I don't know in which extent it could affect. But this could be a difference between Atlantic salmon and Pacific salmon.
Great. And I had sort of a couple questions on both sort of how in your existing simulations you were modeling selection, and then sort of what the kind of realistic capacity for doing that differently in the future might be. So one thing, just, you know, a minor comment I had, but I was wondering, so sort of early on, you have the sort of the growth potential is itself, and that's the selected trait in your model, is the growth potential. And you sort of have that as an emergent property based on, you know, this sort of trade-off around growth rate and survival, and then survival both in freshwater and in the ocean. And then there's sort of a fecundity payoff, you know, an ultimate fitness payoff that's based on size and, you know, sort of based on female egg production. And I'm wondering, you know, have you thought about how you might model the sort of payoff of size differently for males? I mean, I know you do have a sort of separate sexual selection component going on, but, you know, would it be feasible to have sort of different growth optima for males and females? And then how might that interact with your sort of later findings, or especially if there's sort of, if there were different growth optima for males versus females, and then might there also be differences in the migration or dispersal behavior of males versus females? Have you thought at all about how those sort of things might all play out?
It's true that this growth potential optimum, so I look at this, it's not easy to understand what optimum is emerging from the model. The figure that I showed is based on like simple simulations I did, but not based on the model. The way to know the optimum emerging from the model is to look towards which value of traits the population is evolving. And I didn't check that separately between sex. So the figure that I was showing is based on both sexes. So there might be differences of optimum between the two sexes because they don't have the same selective pressures. For the female, the fecundity is related to the size, to the weight. For the males, there is a selection on anadromous males based on their weight too. But for the precocious males in the model, it's not based on their size or their weight. So there might be some differences emerging from these differences between the two sexes. But I didn't explore that, and maybe I should.
Great. And that sort of maybe sets up my next question, which is, do you have any thoughts on sort of, you know, just as sort of a tractable modeling frame, or, you know, using your model framework, is there, I mean, there must be some sort of upper limit on how many traits you could simultaneously model selection on. But, you know, as you're interested in some of the questions brought up earlier about, you know, you sort of have identified this seemingly optimal level of dispersal from sort of a, you know, almost a group selectionist, sort of what maximizes population size or stability of the metapopulation context. And that's sort of, it's very interesting to me that, you know, the sort of optimum you identify at that population level seems to match, you know, fairly closely to what you think or what you've estimated the actual sort of dispersal rates in the field are. And so I was wondering, you know, if you did model selection on sort of an individual's sort of propensity to disperse, one, I was just wondering if that, you know, would show, if your model would also predict selection towards that same optimal level of dispersal, if there might actually be conflict between the optimal individual level of dispersal versus sort of what would, you know, be the sort of group selected level of dispersal, which got me interested. So, I mean, one would just be, you know, could you run the model where sort of propensity to disperse is the single trait under selection? But then I was also thinking, well, could you actually sort of model, you know, the trade-off among different traits, you know, evolving simultaneously? And especially, you know, I got thinking about this because, you know, we were talking about this concept of dispersal being linked to the marine phase and being linked to this decision to smolt. And so could you have sort of indirect selection on the ability to disperse through selection on things that affect smolting behavior, but then also could you have sort of simultaneous evolution of both the propensity to smolt and the propensity to disperse, given that you had smolted, and just sort of how many traits could you have under selection in your model before it gets, either computationally intractable or just impossible to interpret the results, even if you can get the computer to spit something out?
I don't know if there's what is the extent of limitations of the number of traits we could have with a genetic basis. That's a good question. But if we have some issues with that, I think we could use some genetic correlation between traits. For example, if we make the assumption that dispersal is related to the smoltification decision, maybe we could have some genetic correlation between the both. But I don't think it would be a problem to add the genetic basis of dispersal while keeping the other traits. And we could see some evolution of all these traits in interaction.
Great. And then I had one maybe in the weeds detailed question about the methodology, which I think may just be, and maybe I either misread your thesis manuscript or there was a change or sort of further elaboration between when you wrote that and when you gave the presentation. But as I understand the presentation you gave today, in your models of the sort of what's the interplay of dispersal and diversity section, so section 3 of your talk, how it seemed like you were modeling in the talk today, you had in sort of all your scenarios, there was a sort of population level like the great. So if I understood the thesis document correctly, in your random genetic scenario in your written document, you had the growth potential in any given population may have been maladapted, but the sort of metapopulation wide average was at the optimum. And it seems like now you're modeling a scenario where even in the random scenario, the metapopulation mean is non-optimal, and it's non-optimal by the same amount that the mean is in the other scenarios, which I agree is sort of probably a better, likely more realistic representation of what's likely to be going on. But I was wondering if you did have, and maybe you just never modeled in the first place what I thought you did, but can you think of is there a scenario where we'd expect a situation where there's maladaptation in each population locally, and yet the sort of global mean is close to the optimum? Can you sort of hypothesize a scenario where that would be the sort of baseline that we'd be starting from?
So for the case of the average over the metapopulation, which could be around the optimum, I would say we could imagine some perturbations that are going in opposite ways between the populations. So the average would be around the optimum. Some hypothesis like this, but the difference with the manuscript, it was just due to this issue of comparison between scenarios that was limited in my manuscript because the average was not the same. But we could imagine that the distribution of populations would be in the opposite ways, and so the average would be around the optimum. Yeah.
Great. Thanks a lot. And so that's been super interesting. And so I would want to close out just talking a little bit about the parallels or potential applications to Pacific salmon, since that's what I work on a lot. But also I got just really excited reading your manuscript and saying, oh, there are a lot of questions that I'm struggling with that I think, are not too different from the questions you were asking here. And so, what would it take to take the meta IABASM and apply it to Pacific salmon? And so as we mentioned already, one change would be the simultaneity versus iteroparity. And another, then I can think of two big differences in the management context. And I'm sort of wondering how big or how much effort it would take to accommodate either of these. One would be just sort of the nature of the fishery in terms of, I mean, I know you have a mixed stock ocean fishery and sort of stock specific river fisheries in Atlantic salmon as well, but sort of the balance is kind of reversed in a lot of Pacific salmon scenarios where often most of the fishery impact is actually from this mixed stock ocean fishery that's not acting on just one river or one population at a time. And also just the overall exploitation rates can tend to be higher. I think you used a maximum of 50%. There are several Pacific salmon populations that have a higher exploitation rate than that. But I mean, would you see any challenges in incorporating a mixed stock fishery into your model, or is that even already there and just not something you focused on?
No, the mixed stock fisheries is not yet included in the model, but in the future version of the model, I think it could be included. But this, even if it's possible to include it in the model, regarding my scenarios about exploiting the source or the sink populations, I think it would require the ability to differentiate between the stocks. So in the model, it could be possible because we can know where the fish are from. But in the reality of fisheries, I don't know if we could be able to differentiate between these different stocks to potentially test these scenarios. So it would largely depend on the possibility to differentiate stocks, I think.
Great. Yeah. Well, that sets up the other big difference I was going to bring up and sort of was interested in your thoughts on, which would be, the large amount of hatchery supplementation of a lot of Pacific salmon populations. So I'd be interested in your thoughts, both just first of all, how would you incorporate hatcheries into the model? But then also, you sort of mentioned this, kind of, and I think sensible, but a little bit sort of counterintuitive or surprising management implication of, maybe we actually want to preferentially harvest the sinks and protect or be less intense harvest on the sources. And I'm just wondering how or if, the sort of having hatchery supplemented populations would factor into that thinking, where you sort of essentially then might say, the populations with a lot of hatchery supplementation on them are then sources. And does that mean then we actually don't want to harvest hatchery fish? We want to harvest, the rare, smaller or sink populations. So I guess just, your thoughts first on how would you model hatcheries, and then would or would that not be compatible with your sort of thoughts on source versus sink population exploitation?
So I think we could implement hatcheries within the model by adding some individuals at, for example, the juvenile stage within the population. But this would implies to know then what is the behavior of this fish, and especially their, for example, growth or survival, which could be lower than wild individuals, their reproductive success. I think this would require a large amount of information. I don't know if we have this information. And regarding the management, the exploitation strategies, considering hatcheries' influence, if hatcheries are implemented in the source populations, this could imagine that they have a good reproductive success. This could increase this rescue effect from source populations if we continue to explore to fish the sink populations. But I don't know, with this idea of wanting or not wanting to fish hatchery fish or wild fish. I don't know how could we consider this, but that could be something interesting.
Great. Yeah, I think you've clearly thought a lot about a lot of these things, and I really appreciate that. Appreciate the chance to talk to you today, and I think that concludes my questions.
Thank you.
Thank you. Then I guess it's me. Do you still feel like answering some questions? Okay, well, I can start also saying that I think you've done great work, a lot of work, as everyone else has also said. Your presentation was really good and clear. I think you did a good job. Working myself also with individual-based models, I know that they're very complex and not always easy to communicate maybe, and maybe not always easy to understand either when you are in it, even if you're in it yourself. But maybe we can start a bit with the individual-based modeling. Like the whole idea is...
Do you want your
Well, it's fine now. I'll start with something, so I'll let you know if I need that, So the whole idea is that we understand the individual, right? And then we upscale it, we make them into populations, and in your case, even into a metapopulation. Mm-hmm. But then throughout the whole thesis, I really struggled finding anything about the individuals, like curves or growth curves, or like, did you present something on the individual level, sort of in your...
In my manuscript?
Yeah.
Just a little bit, I think, in the chapter describing the model, but not in the introduction.
Yeah, but do you like when you're working with the model, do you look at the curves, like how an individual growth trajectory, for example, looks like, or do you more concentrate on the population level?
I would say that only when I have issues, and I'm not understanding what's happening, I look at some individuals and their trajectories. But otherwise, I only looked at the population or metapopulation results.
Yeah, because at least to me, it often kind of gives me more trust to a model. Yeah. If I can see, okay, what are the basic blocks in the system actually doing? Yeah. Because then on the population level, things might... you can have a portfolio effect in a way that some things are doing something and other individuals are doing something, but on average, it looks like okay. So maybe that's just a suggestion that in future manuscripts, it might be helpful also show some what are the individuals actually doing.
Yeah, I tried a little bit with the immigrants versus philopatric individuals, but that's it.
Yeah. So it's just a suggestion for, I at least find it helpful. Then I was struggling a bit understanding the heritability in the model. So you said somewhere you used the 0.14 heritability, and then somewhere it was 0.4.
Yeah.
But is sort of the input heritability, or
But so it's like the variance, the environmental variance that we put on the computation of the phenotypic traits based on the genotypic traits. The variance is defined based on this initial heritability.
Yeah. Have you looked at the emergent heritability?
Not really.
Yeah, because you also have density-dependent effects. Do you think that could affect the heritability?
Yeah, it might. I think it might affect the heritability by playing on the phenotypes. Yeah,
because it might have an effect. So it's again one of the things that might be helpful to check, like is your heritability actually what you think it is? Because of course heritability is the key how fast your model is evolving.
Yeah.
Because if you have very low heritability, nothing changes. And if it's too high heritability, then things can go really, really fast. So again, maybe just a suggestion that it can be helpful for also the readers to kind of consider the model. How is it working? Maybe if you put the slide, I have some of the slides. I don't know where they are. If you could put the slide number 3. It's about the growth optimum. Because I still, even though someone asked about it, I still struggle understanding what's happening there.
Here.
Yeah. So where does this optimum come? What are the drivers optimizing this?
Okay, so I think it is mainly this river survival.
Yeah. So that's a function you plug in the model.
Yeah.
Yeah. So and that's same for all the individuals.
Yeah, it's a trade-off between growth and river survival.
Yeah.
The second one is sea survival, which is strongly dependent on the size of individuals, so related to growth potential.
Yeah.
And there is also the fecundity of females, which is related to their weight. So that's the main processes that are implemented that I think drives this growth potential optimum, but there might be other factors in the model playing on this optimum. But I think these functions are the main drivers.
But I've understood that the model, because and I understand because they're doing a daily step, so it's heavy to run. But have you run the model for a long time to see what the actual optimum is?
So I only run the model for the main of my simulations for 50 years, so 20 generations. It seems that the population stabilized around this value. When I put this shift, so the populations are maladapted, it seems that they converge around this. I don't remember if I checked for example, 100 years.
Would it be possible to just make one run and let it run for, I don't know, I run my models for like 300,000 years.
Okay.
to see what happens. Okay. And sometimes things happen late in the something, and I have had more traits, which makes the evolutionary dimensions much more. So then more things can happen, whereas you have fewer traits. But I think that might be also helpful, because now I'm it's because when I'm been working with my type of model, of course I kind of think in one way and you're thinking the other way, and I'm trying to kind of find the connections, what are the similarities and differences. But okay, so I do understand that this is based on the equations you put into the model, that this is what you think is the optimum, but you're not sort of 100% sure.
On 50 years,
yeah,
it is.
But can you put can someone, I don't know where my slides are. Yeah, so the number 2 is just
yeah.
So like here, for example, in the first one, some of them stabilize much lower levels, and some of them seems to, in the 15, they seem to be leveling and then a higher. Like, is that how would you explain these differences?
I would explain these differences by the influence of immigration, which largely drives the evolution of the populations. For example, this one, it seems that the population is evolving towards the immigrants' traits.
Yeah, but why do they have different traits then?
The immigrants?
Yeah.
Because they are coming from different populations with different initial conditions.
Okay, but I guess I'm trying to ask, do you think all the populations are supposed to have the same optimum?
Not necessarily, but in these simulations, it seems that they had, because we set up the same parameters for all the populations, driving these relationships that we saw before. So I think it drives strongly this optimum, but due to density effects or other factors, it could be different between populations.
Yeah.
But it's true that I did this hypothesis by putting this optimum line, but I'm not sure yet.
Yeah, I'm just, because as I said, I struggle a bit to understand what are all the things that are sort of driving the evolution. And here it's kind of like, said that, okay, here is the optimum, and then I don't quite understand how you get to that optimum. I mean, I do understand, like you say, that you have these equations and then you come up to this, and you've done some modeling to find this optimum. So I'm just, that's what I'm kind of...
Yeah, maybe it's not good to say there is this optimum. I should say it might change, but in these simulations, it seems that it's converging towards this value.
Yeah. And I guess it might be, I mean, are there some differences? There are some differences in between the populations. I mean, there could be different optimums.
There could be,
Yeah, but you're not sure.
But my scenarios were quite parsimonious. We had the same environmental conditions on average. We had the same, except these scenarios, the same distribution of traits at initialization.
But the density is different.
The carrying capacity.
Yeah.
So the potential number of individuals, but the density could be similar between populations.
Or different.
Or different. Yeah.
Well, that leads to the next question about density-dependent effects. Because you said also that you started your simulations with 25% of the carrying capacity. And in my experience, and I think also looking at your results, having low density has, it releases kind of the pressure from the evolution because they get it for free in a way. But does that have an impact have you thought about that? Like when you start at a lower population density, that you kind of
So I think that in my simulations, I reduced the carrying capacity for the size of simulations. So the density should not.
Okay, so it's just that sort of the number of individuals who stay down.
The number is lower. So this could affect, for example, the extinction risk or rescue effects. All of this could have impact on results. I think density.
Okay.
The same.
Okay. Well, then I probably just misunderstood. Okay. Yeah.
That is it.
And then if we just look at this picture, so the gray area, can you remind us what is the gray area in the beginning?
The gray area.
Yeah.
This in these scenarios was the running step, so without dispersal.
Yeah.
In these simulations, we only studied the possibility of dispersal after 10 years.
But then, like in some of the cases, like in 8 and 10, there is changes already before you allow the dispersal.
Yeah, this is due to selection towards this optimum.
Yeah. Yeah. Okay, and that's because you push them away from the optimum.
Yeah.
Yeah. Okay. That's another thing that is sort of, I think, tricky with evolutionary models, because there is an evolutionary optimum somewhere, right? But if you jump on the trajectory, then you can't be sure what you are studying. Do you understand? Like if you, for example, are looking at the effects of fishing on evolutionary life history traits, and if there is a trend in your traits, and then you start fishing here, you can't be sure whether the model is still, or the population is still sort of adapting to or just trying to find the optimum, or is it actually the effect of? So that's why I'm kind of like, what's going on there? But then it's because you expect it already, because you push them away from the equilibrium.
Yeah, I expected already.
Yeah. Good. Thank you. Let me see. Many of the questions have already been discussed. I actually wanted to ask about something that was discussed also a bit about the management issues, like the sink populations maybe would be most in conservation sense maybe best to harvest. But did you look at the catch?
You mean the number of catch?
Yeah, like how much you kept?
No, I only looked at the rates of exploitation.
Yeah.
So the proportion of the metapopulation that was exploited.
Yeah.
So we could expect differences in the number of catch. But I looked at the exploitation rate because this is the metric which is used, I think, for management.
But if you have a big population and you have an exploitation rate of 10%, and you have very small and have an exploitation of, so maybe the catch is quite different than from the management, or kind of if someone actually wants to fish. What do you think?
Yeah. Maybe they will not be happy.
Yeah.
But the metapopulation might be more stable in time, and I don't know. Maybe it's a trade-off.
Yeah, but maybe just from kind of the management side, it might be often that the catch actually is also an interesting thing to look at. Because, well, basically, if you want to manage for harvest, you actually are often interested in the catch, even though exploitation rate would be the metric when you plan the harvesting.
Okay.
Yeah. Let me see. I'll see if I have some more left here. You also talked in some of your papers about conservation, what to wear when. Because you kind of say like it would be nice to use, for example, your model into kind of trying to answer or help in this kind of decisions, right? But do you think it's is it a question for biologists like us, or is it a question for someone else?
You mean to investigate these questions of management?
Yeah. I
think it's. I would say it's one objective also of our job to inform management, to help pointing what could be important regarding the functioning of the species, but then to take the decisions. I don't think it's our part of the job.
Yeah. Very good answer. Very mature view of the role of scientist. That was good. Okay, I think we should go towards end. Let me see. I have maybe 2 minutes left. You talked about fishing-induced evolution, and I, as you know, have been working with it. And you mentioned at least in 2 occasions in your thesis that fishing-induced evolution is due to selective harvesting.
Yeah.
Yeah. But what do you think happens with random harvesting?
It could also be a selective pressure, but if it's not on the same type of individuals, I would say it would have selective effects, but maybe with variations in time or in space. Yeah.
Well, if you think that you would have random select, right? So then for any individual, the likelihood of surviving to old age would be reduced.
Yeah.
Right. And if you think about things happening late in life, or if there are, let's take maturation, that's always an easy example. You would say, okay, it would individuals that would mature late in life.
Yeah, that's what I showed in my last part. We don't have selective harvesting regarding once in winter or supposed in winter, but we see this evolution of the growth potential, which could suggest that the precocious maturation strategy be selected for, and so the migration to the sea selected against. But I consider that it's still selective harvest on adults rather than maybe juveniles, or even if I know that it's not the case, but.
Yeah, well, I mean, we've done modeling studies on this, and it's and other people have done it too. But it's because it reduces the lifespan.
Yeah.
It makes the life cycle faster because things that if you would mature at 20 years and the likelihood of surviving there is 0.001, those genes will not go further. So just a little thing.
Yeah, it's still selective.
Yeah, so it can still cause evolution of the life histories, even though it's not selecting certain type of individuals. Okay, I think I should stop. Time went really fast. Enjoyed discussing with you, and I think you've done a great job. Okay, now I think I have some some chair tasks here. I have to read from my list.
So now it's for the supervisors.
Yes. Okay. Let's ask the supervisors to enter the floor.
So I'm gonna give you some context and some words to describe the Amaya works, and also probably Stephanie after that, if she has a few words to add, she can intervene. So, but first of all, I would like to thank, of course, the members of the jury. For accepting and evaluate the massive work of Amaya, especially the 400 pages and the 1 kilos. And I didn't wait the manuscript, it was a good idea. And so I would like to thank the jury members, especially the one coming from far, the one who are sick today, the one who woke up at 5 in the morning, and the one who has teaching duties. So thank you all, and thank you for your questions. It was very interesting. So some few words to give some context of the work of Amaya. So the project began long time ago, actually, when I arrived in the EcoBiop group. It was a project which stems from a reflection we had with Stephanie a long time ago about the portfolio effect, which, as Amaya mentioned, is well studied in the Pacific salmonids populations, but less in Atlantic population, and I think it was already very interesting to start evaluating this in Europe. But also, so we decided also to, because Stephanie and I have been interested into dispersal strategies, and we thought it would be a good idea to combine the two, and which led to the idea of the adaptation network. And so, based on this project, we started with 2 internships, one with Lauren and the second one with Amaya, who contacted me to do internship abroad, and so she contacted Stephanie and Peter Wesley, and so we thought it would be a good opportunity to start this project, especially regarding the portfolio effect and the dispersal. And so we got lucky to have funding for the PhD, and so Amaya continues these projects and push further all the questions we had. But to carry out this project, so you had Amaya to be more familiar with different type of modeling approaches. So she presented the work on the interval-based model. She contributed to develop a new one. But also, she also played with a statistical modeling framework with some Bayesian analysis, especially regarding the temperature and the flow of rivers, which we initially were very interested to look at the response of population to climate change, but we realized it was a lot of work and a lot of missing data. So we gave up, and we've been more interested then to the combination of dispersal and diversity. But just to point out, so Amaya did a lot of work, spent a lot of time also to explore this effect of climate change and play around with different kind of approaches. You had also to better understand the IBASAM model, which is very tricky, especially when you don't know, you didn't code the model at first. It's very difficult. It's like going into the mind of the developers and their own architecture, their own thoughts, and so it's a very difficult work. But you did it very well, and you also improve a little bit the model as well. And at the end, you being able to develop the model and bringing the new ideas you got during your PhD. And also, one of the difficulty was to deal with many concepts, theoretical concepts in ecology and evolution, which probably you didn't have all the background for that, but you have been able to tackle all these challenges all together, and so it was very impressive, actually. And so also, so you show us some of your results, but you tested many scenarios, and with a lot of parameterizations and many simulations. You create a lot of data sets you had to deal with, and which led to many exchanges of ideas and brainstorming together. especially late in the afternoon, sometimes on Friday. But it was always very interesting and rewarding and very exciting. So it was a real challenge, but you managed to master it brilliantly, I would say. And so you did everything in the context of COVID, so you didn't have to do any experiment or field work, etc. But still, for many of us, it had a huge impact. But I think you managed to deal with the situation very well. Even if we had to change the plan, especially regarding the missions in Berkeley and the interaction with Stephanie, we had to find another way to work all together. Some conferences you didn't have the opportunities to go, but at the end you managed to anyway to go back in Berkeley after the COVID, and especially getting a Fulbright grant where you applied, and which is again, congrats, because it's a very prestigious grant. And then what I could add, so yeah, you also during so your PhD, the 3 years, so you had also a lot of trainings, some teachings as well, and also you organized twice the no-pass meeting. So it was also very impressive, and also you were part of this group of the Demogenetic network, and you invested a lot of yourself, and we can see with the paper. And so again, it was very impressive. So at the end, so your work will be continued, I hope, especially with a lot of ideas you develop and propose, and also with the ideas from the member of the jury. And just to finish, I would like to say it was a real pleasure to work with you. I hope you are very proud of your work, because I am very proud of it, and I wish you the best for the future.
Thank you.
So I'll let Stephanie, if you have some words to add.
Sure, I'll add a few things. Matt, you covered a lot of the things that I wanted to say, but maybe just a few things I'll add on top of your comments. One, Amaya, it's fun to kind of think back about the evolution of our discussions and ideas. I remember from your first visit in Berkeley, when you decided to extend the IVSM model to the metapopulation level, that you had many, many ideas about aspects that you could focus on for your dissertation work. And I remember that it was almost kind of dizzying, the number of directions like you could potentially go. And to think back on those original conversations and how you sharpened your focus around these particular dimensions is very impressive, including today's presentation, which several members of the jury highlighted. It's even a sharper focus today, I'd say, than in the dissertation itself. So it's very exciting to see the evolution of those ideas. I also just think that the body of work is really impressive, and that it includes theoretical advances addressing sort of general questions in eco-evolutionary dynamics, methodological advances extending the IVSM model, and then of course the management implications. It's a very just cohesive and coherent body of work, and I hope you feel really, really proud of that. I also want to echo Matt's comments about COVID. I think this body of work is all the more impressive given the many sort of setbacks that students and supervisors have faced over the past few years. And I found that you were, just very sort of versatile and took all of that in stride. And I appreciated your efforts to stay in contact via Zoom and to keep in communication. And I especially appreciated our visits in Berkeley and the chance to spend some time in the field with you in Berkeley as well. So I also just want to say you've been incredibly efficient. 2 papers published this year, with another paper almost submitted, as I saw on your slide. I think the only thing in between that submission is holding you up was basically today's defense. I imagine that's going to go off pretty quickly. And another that's on the way. So a very, very impressive body of work. I've really enjoyed the chance to work with you. Really proud of everything that you've accomplished, and I'm excited to see what you're going to do next. So congratulations again. And I also want to thank the members of the jury. I really appreciated the questions today, lots of ideas.
for future extensions, and I really appreciated your careful read and the thoughtful questions that you brought today. Thanks again.
Thank you, Stephanie.
Okay.
Yeah. So now the public can leave the room, please. So for the jury to deliberate. I could have said that in French. Merci.